Let's solve the differential equation y double prime plus 4y prime plus 4y equals 0. This is a case of repeated roots in the characteristic equation. First, we form the characteristic equation. R squared plus 4r plus 4 equals 0. Notice that this factors as r plus 2 squared equals 0, giving us a repeated root r equals negative 2. Therefore, our first solution is y1 of t equals e to the negative 2t. Since we have a repeated root, we need to find a second linearly independent solution. We'll use D'Alembert's method of reduction of order. We assume a solution of the form y equals v of t times y1 of t, which is v of t times e to the negative 2t. The first derivative is versus prime times e to the negative 2t minus 2v times e to the negative 2t. The second derivative is versus double prime times e to the negative 2t minus 4v prime times e to the negative 2t plus 4v times e to the negative 2t. Now we substitute these expressions back into the original differential equation. After substitution and collecting like terms, most terms cancel out, leaving us with v double prime equals 0. We integrate twice. The first integration gives versus prime equals c1. And the second gives versus equals c1t plus c2. Therefore, the general solution is y equals c1te to the negative 2t plus c2e to the negative 2t. Our fundamental set of solutions is e to the negative 2t and te to the negative 2t. Let's verify these are linearly independent by computing the Wronskian. The Wronskian determinant is e to the negative 4t, which is never 0, confirming linear independence. Let's plot some typical solutions with different initial conditions to see the behavior. For repeated roots, the general solution includes both the exponential term and a t times exponential term.